Okay, so I was asked to give a talk on remote sensing of clouds and precipitation, and the backdrop there is the A train. And when I proposed CloudSat in 1996, and again ultimately in 1998 when it was successfully selected, I believed at that time that a suite of measurements with CloudSat, such as now available with the A train, would have a fairly profound contribution to the aerosol indirect effect as we thought about it in warm clouds. And I'm going to try to convince you of that as we go along towards the end of this talk. I think this is the right hand button. Okay, yeah. Okay, so the remote sensing of clouds and precipitation, one tends to, and I've got a couple of just sort of pedantic, heuristic kind of view graphs here, but it's well to dwell on some of these aspects as we think about the performance of what we can do today and perhaps what we might be able to do in the future. The remote sensing of clouds and precipitation, there's still sort of, I guess you could think of it as two broad flavours, or passive and active. Passive systems rely on obviously radiation emitted or attenuated through the atmosphere, and active systems are involved in transmitting power and receiving the power and measuring properties of that power, including polarisation, phase shifts and so on. Where we've made significant strides in the last decade or so, I would guess, the last decade in particular, is that it's not one system or another, but the integration of systems that really tells us about unique aspects about the Earth. And I'm going to try and convince you that combinations of observations actually gives us clues about processes and how processes evolve in the atmosphere, particularly as it relates to the aerosol indirect effects. I'm going to skip over this. So sort of broadly outlined, I'm going to talk a little bit about the capabilities of passive systems, just very broadly. Active systems, a little with sort of a smattering of sort of highlights, and some more advanced systems which are integrate the two to tell us a little bit about warm rain processes and aerosol indirect effects. Since it's sort of the topic of the meeting, I will apologise. I didn't. If I was more thorough, I would have included ice clouds. Clouds other than clouds with water in them. Well, they've all got water in them, but clouds other than liquid water in them. But the tenor, most of the tenor is to do with liquid water. Okay, so microwave systems. So microwave systems, sort of the physics is as follows. Essentially, over the oceans emit, appear to emit at a very cold temperature. The emissivity of the oceans in the microwave isn't unity. And so they look cold, and as you get an emitter from the atmosphere that sort of overlies that cold ocean, the emission increases, and that differential between the ocean and the atmospheric emission is the signature of the emitter, in this case the clouds and the precipitation. So from that difference you can extract, because of reasonably strong contrast, you can extract information about the water path of precipitation, water path of clouds. This doesn't work very well over the land, where the contrast is much, much weaker. And in fact, I would contend that it sort of doesn't work over land much at all in the microwave, although there's industries out there trying to use microwave over land to get precipitation and other properties. Obviously, soil moisture is one of the properties you can get over land. But as far as the atmospheric information from the microwave emission, the contrast sort of almost denies you the ability to get information about the water species in the atmosphere. So it's the passive microwaves, essentially powerful over ocean but lacks over land. And that's kind of an issue, because when you want to look at cloud aerosol interactions and you would like to be able to contrast land versus ocean kind of behaviour, you've got this nagging problem always when microwaves involved that is it purely an artefact of two different physical approaches to get properties over land and properties over ocean. Just an advertisement. There is microwave observations, or passive microwave observations have been in existence since, before RAM was even at NCAR, I think. It goes back in the early 80s. We probably are well over 30 years of these microwave observations now. And now, in what's been developed in progress here is the development of a climatology of cloud liquid water from microwave radiances over oceans. And you can see the preliminary results from this climatology is being developed in combination with CSU, who are working very diligently on the fundamental data record, the radiance data record, to kind of make sure the calibration's stable throughout the 30 years, and a group at JPL who are also looking at the retrieval information and making that homogeneous. So this is a sort of a snapshot of liquid water changes over the oceans for the last 30, not quite 30 years, there's 25 years in this data record there. So you can just got to whet your appetite that we have now a fairly extended data record here on liquid water path, and the question I'm going to get asked is how good is this? And we'll get to that in a second. Precipitation. When you try to extract information from these observations of microwave radiances, visible radiances, near-infrared radiances, you have to basically construct a model of the observing system. And the simplistic approach is you match one against the other, the observations and the model of the observing system, and then you optimize the solution to minimize the difference. What's typically not ignored is the overlooked importance of the model. And it's not just the radiative transfer of the model in this case. In this case, I want to highlight, in the case of precipitation, this is a model of the atmosphere, of the precipitating atmosphere that's been used widely to develop microwave radiance-based precipitation. This is a so-called quote-unquote Wilhite model. And you can see how simplistic is the structure of the atmosphere and the precipitation. It's very, very idealized, and this in itself is a source of huge uncertainty and ambiguity in terms of understanding the observations. And so if you look at the basically raw relationship between microwave radiances, brightness temperature here, and surface precipitation, you can see this is at 10.6 gigahertz, you see quite a range of spread in results. So if you have any one measurement of brightness temperature, what the heck's the precipitation? And the reason it's spread is because the vertical structure of the precipitating atmosphere matters and influences this signature. So the approach is to use this quote, if you're in trouble in remote sensing, you always rely on a database. That's how you get out of trouble. So in this case, they rely on a database. And so this basically shows you a profile database that gives you the same value of precipitation at one of these ranges here. So there's real degree of ambiguity here with respect to the passive. And so part of the challenge is always to remove this ambiguity. So I'm not saying it's futile, but the uncertainties in precipitation, from passive measurements, you have to assume they're of the order of 30% or more because of these kinds of ambiguities. Now, one of the issues with using microwave for getting cloud information and precipitation information, and one that's sort of not clearly sort of stated in the literature, is the fundamental question, is it raining or not? You have to make that decision. And that's pretty important. And it turns out for the indirect effects, that's quite fundamental to know whether the cloud's raining or not, because it really shapes how aerosol might influence the clouds. And so from a microwave perspective, the typical approach has been that at some defined threshold of liquid water path, such as shown here, and this is actually a slice of a precipitating system that's seen by CloudSat radar and by the AMP-SARE radiometer, all flying in concert in this A-train. And the AMP-SARE drives the liquid water path, and at some liquid water path threshold of, let's say, 200 grams per centimetre squared is roughly the threshold, it's decreed that there shall be precipitation and that it's no longer cloud. This is actually a big, big issue for all of our remote sensing observing systems, is how can we see this transition from cloud to rain? The radar, as soon as you get rain, it blocks the clouds. Clouds no longer visible. These passive systems make an arbitrary decision. This is a fairly big challenge for us. We haven't got the solution for this, although bringing different sorts of observations together gives us a bit of a clue, but by no means definitive. Okay, so is it raining or not? So they use this threshold, and this gets one into trouble. And one of the examples is over here of the west coast of China, where this shows you an example of a microwave radiometer shows lots and lots of rain falling because there's lots and lots of liquid water when they initially do the estimate, and so there therefore must be raining. And it turns out the TRIM radar, which is also flying with this observing system, shows no rain at all. And the reason for that is an aerosol signature on this. The aerosol has shut down the rain process, and these clouds have very large liquid water paths, and these algorithm says, therefore, it must be raining. Of course, it's not. So I sort of point this out because this is sort of one of the challenges for us in terms of designing observing systems that might want to go after understanding the processes that are really central to the aerosol indirect effect. One of the things we can do, and we have been able to do with this sort of exquisitely sensitive spaceborne radar called CloudSat, is we can pretty much tell you when it's raining and where it's raining, how often it rains. We have trouble telling you how much, particularly at the high end. We can tell you how much at the light end, but how much in the high end is a bit of a challenge. So this is a map of the probability, global probability of precipitation. Tells you the percentage, so you can see down the southern oceans. It's kind of raining. It's kind of raining 30% of the time. It's precipitation is 30% of the time. This is what in the talks this morning. You saw use of these data in terms of analysing aerosol indirect effects and probability of precipitation in the context of probability of precipitation. That's what this is. Okay, I kind of can skip over this, but these are various different products of precipitation that you probably all may have used. There's the PR, this is the AMSA-E product. I've got to get this right. This is the PR product of the trim, AMSA-E, which are the microwave radiances. AMSU and MHS is a precipitation derived from that. This is the OLR-based precipitation, which is widely used in climatologies. And this is the CloudSat probability of precipitation, which we can sort of take as truth, although, we still have to question that. And this is the CloudSat. There's 4 different values of the probability of precipitation of CloudSat because they match to the appropriate resolutions of these different instruments. So you can see that, in terms of the frequency of precipitation, we have some of these observing systems have some really kind of serious, I would argue, serious flaws, but that's another problem. Okay. This is an issue. This is a cause for concern when we come to thinking about aerosol indirect effects and warm clouds. I've been arguing for years now that I view this aerosol indirect effect and warm clouds as fundamentally, first and foremost, a problem of understanding the water budgets of clouds. I see no reason to change my mind. This is cause for concern. This shows you the precipitation bias. This shows the same thing for different models. I'm just going to focus on this one. This is a very recent figure from ECMWF using 2 different versions of the model, very recent versions of the IFS current forecast model. This is the bias in precipitation relative to the SYNOP data, which is a sort of a kind of a global data set that they use, a surface precipitation data set they use that they ingest into the model. And so you can see the well-known drizzle bias here. The models drizzle all the time. And they have a heavy rain bias here. Where they drizzle too much there, their heavy rains tend to be sort of too light. We sort of know why this drizzle bias occurs. We think we know why it occurs, and we've been working with ECMWF to remove this with some exploratory versions of the model which aren't yet in the forecast mode. The problem is that when you remove this drizzle bias, it makes their forecasts worse, their skill scores get worse, and they don't implement that as an operational system because they can't implement anything that makes the skill scores worse. But we sort of have a handle on why we think this is the case. But nevertheless, this is a real issue because I believe that, as Rob talked about before, that the drizzle is a very fundamental process for understanding the warm rain aerosol indirect effect. And global models with this drizzle bias, a fairly major bias, as I said, is a cause for concern. Okay, getting on to away from the microwave into the solar, into other channels, the solar channels. This is sort of microphysics done from reflected sunlight, and it was sort of an idea sort of introduced by Sean Toomey back in the 80s and popularised by Nakajima and King in the 90s. And basically the idea is you measure 2 wavelengths, a visible wavelength and a near-infrared wavelength. The visible wavelength tells you about the optical depth. The near-infrared wavelength tells you about some combination of the optical depth and the particle size. It's buried in there, but believe me, it relates to the particle size. So you have to have the visible to unscramble the optical depth dependence of the near-infrared, which now allows you to then unscramble the particle size information. The relationship between these is optical depth is proportional to liquid water path divided by particle size. This is a relationship I introduced back in the late 70s. So measurement of reflection of 2 wavelengths, 2 spectral bands returns a pair of parameters, optical depth and particle size. Now, You can slice it any way you want. You can change this. There's two pieces of information about the cloud system. Some convert this to number concentration by you introducing assumptions about adiabatic properties of clouds. There's really only essentially two pieces of independent information. How you sort of slice that, where you want to convert it to something relates to number concentration or effective radius, is kind of a choice actually, but it's you're limited by the information. So coming back to the microwave, coming back to the microwave, and the what's shown here is a Modis-derived liquid water path using this optical method, the microwave liquid water path using the microwave method, and this is data over the whole globe when conditions are right. And what I mean by conditions are right, that means when there's no drizzle, this won't work in drizzle, when the footprint of the microwave instrument, which is a few kilometres, almost 10 kilometres, is full of clouds, there's not partially broken clouds. Under those conditions, these tend to agree pretty well, which tells us there's two different physics. This is physics. This is scattering. This is emission physics. We come up with sort of the same answer under idealised conditions or somewhat idealised conditions. So it tells us that we're kind of probably right in the interpretation of it. On this table here are sort of global numbers, the liquid water path on drizzling clouds, the liquid water path on all clouds, and so on. There's two different cloud particle sizes here, a 2.1 micron and a 3.7 micron derived particle size. This is kind of important because this has led to a lot of confusion over the years about cloud droplet effective radius and, which one do we use. And so I'm going to talk a little bit about that now, I think. Yeah. So this is an example of three of the cloud droplet effective radius in warm clouds derived from three different channels of an instrument. In this case, it would be Modis. I think it's Modis. It might be the GLI. I can't remember now. 1.6 micron, using 1.6 micron as that absorbing channel, that particle size channel. 2.1 micron or 3.7 micron. You can see that particle size is the same scale. And I apologise, you can't see that. 14. I can't even see it here actually. This is 24 here. That's 14 microns there, and this is sort of 8 microns or something there. 5 microns down this end. Anyway, the particle sizes are very, very different, and this was Paul's concern. It turns out this is actually geophysical. There's information about the cloud system here. This is my argument. There's others that argue that it's just sort of a spurious effect of three-dimensional effects of clouds and all sorts of other stuff. I think that's gobbledygook. I think it's fairly simple. It matters because these observations are often used to contrast the model and even used to help tune models and indirectly the cloud indirect effect in warm clouds. Okay, so this is why I think it's physical. This shows you a nice analysis that was done by Nakajima et al. And Kenta Suzuki and so on. It shows you the composited data, shows you active and passive data combined together. Radar reflectivity on the, go back here. Radar reflectivity combined on the x-axis, optical depth on the y-axis here. And basically, when the Modis says the particle sizes are in the bin between 4 and 10 microns, this is the sort of reflectivity profile that you get. No drizzle, it's all cloud mode. Drizzle, just to calibrate you, this is minus 20 dBz, that's cloud mode. Drizzle is somewhere between minus 15 and 0 dBz, and rain is 0 to 15 dBz nominally, okay? So just to sort of calibrate. As you can see, as the particle sizes increase, you transition into drizzle and then into rain. This is something that you would expect. It's intuitive. It seems reasonable, and so I argue that the particle effective radius and the large effective radius that you see in the observations are signatures of drizzle everywhere in these warm clouds over the oceans. Okay, so this is an example of the same analysis done over ocean and over land. It's actually interesting. This is very preliminary stuff that we're just producing. Shows you that over land, over ocean, the clouds transition and there's a prevalence of drizzle, and then you get into the rain where you get the larger particle sizes, but there's a lot more drizzle in the oceanic clouds. These warm clouds over land have much less drizzle than over land clouds. Warm clouds tend to go from cloud to rain, probably, and it's because of the stronger vertical motions associated with the shallow clouds over land and over oceans. This is the ARM data broken up and analysed the same way to sort of convince ourselves that these signatures we're seeing also reproduced in a totally different data set with surface observations. The next diagram takes the ARM data and breaks it now into vertical motion. So you see this transition from cloud into rain, into precipitation, and you can see a transition from very weak updrafts to very strong updrafts as you go into the rain. So you can start to see signatures of processes going on here, the dynamics. This is a poor man's attempt to get vertical motion from an observing system that's not vertical motion capable. And we'll come back to that in a moment. I must skip over that. Okay, so the last part is the aerosol indirect effect and related processes from these observing systems. So the idea is we'd like to be able to go from particles, information about particles being nucleated, aerosol number, concentration, species, vertical motion, for example. We'd like that sort of information. We'd like to go know something about the condensational growth and then the coalescence process and the precipitation, ultimately, and efficiency of precipitation. We'd like to sort of understand this loop, and can we do that, attempt to do that in any way from an observing system, even from space. And what I suggest to you is that we can see parts of this process by judiciously using observations, and I argue that these might provide a sort of a strategy or a metric for testing models against. I'm going to skip over this, but this is kind of complicated. Basically, let me cut to the chase. This is the optical depth, is vertical coordinate system. So this is clouds composited, a bunch of optical depth and radar reflectivity, like I showed you in the previous diagrams, and it shows you the transition from cloud into rain. It turns out, you go through this analysis with a simple one-dimensional cloud model, and the slope of this relationship relates directly to the collection efficiency. So this has signatures of this coalescence process in the way these two data sets are constructed and correlated together. That's the essential point. So when you take these data, you can now take these sort of analysis. We have observations along here, binned by particle size. We have a model, global model. We have two global models analysed in exactly the same way. And this is now a test of the way in which the processes of cloud to drizzle process is unfolding in the observations compared to the model. And what you see straight away is that there's a distinct cloud mode that's transitioned slowly into drizzle, but the model immediately has drizzle. So as soon as you get some liquid water, it immediately goes into drizzle. So this is sort of consistent with the perpetual drizzle bias of the models. This matters, we think. This is a result from Chris Stolat's paper 2013, which probably many of you have seen. Basically shows you the historical temperature record run with three different assumptions about this drizzle, the turn-on of this drizzle process. And this is the A-train observations. This is when they change the critical radius in which the precipitation gets turned on from 6 microns, which is the standard model, to 10 microns, which is the closer to the observations. And when you do that, you basically get a much colder temperature record. It doesn't look like the observations. So, wouldn't you know it? The more realistic is the physics, in this case the drizzle physics, the worse the climate simulation. It's a little bit like ECMWF not wanting to degrade their forecasts, for obvious reasons. Okay, so we'll skip over that. How long do I have? I'll probably wind up, is it? That I don't know whether... 5 minutes. Okay, let me go into more about the aerosol indirect effects from a remote sensing perspective, and in this case, using ship tracks as a kind of a surrogate for looking at aerosol indirect effects. Just as a kind of a sort of an anecdote, this figure here is a figure of cane fires in northern Queensland where the smoke gets ingested into cumulus clouds. These are the clouds that Sean Toomey studied and discovered the Toomey effect, basically, in this part of the world. So I took that when I was up there. I was snorkeling the reef, but I thought I'd take the picture. Anyway, you think about the Toomey effect and unadjusted forcing. You can think about the direct effect on the albedo of clouds as proportional to a change in optical depth. Proportional change in optical depth is one component due to proportional change in liquid water path and one change due to particle size part. And this was sort of discussed early this morning with respect to Steve Gann's talk. We're looking at ship tracks. We had this student who collected 3,000 ship tracks from the A-train. There's combinations of LiDAR and radar and MODIS and all sorts of stuff that you can composite together. It's an incredibly valuable data source, we think, that could be made available to the public. The unadjusted forcing is aerosol smaller drops, increased optical depth, increased albedo. That's sort of the argument of Toomey with the liquid water path being held fixed. And again, it's all about the liquid water budget of the clouds and how they change. There's two other components to this that you might think about. This may be sort of too simplistic a way of thinking about it, actually, but one has to do with lifetime effect where the liquid water path now changes, and another part is the entrainment effect where the liquid water path also changes through evaporation, where you have a liquid water path change. So the water budget's changing in these two scenarios versus the one before. So this is sort of a synthesis of the ship track data. It shows you here the change in the albedo of clouds versus the change in liquid water path of clouds. And you can see there's a very distinct relationship between the change in liquid. This is in the ship track, out of the ship track. That's the difference here. So in the ship track, out of ship track, change in liquid water path, and in the ship track, out of a ship track, change in albedo. You can see that the change in albedo tracks, as we would expect, very much proportionally with the change in liquid water path. But what you find is that what happens to the actual ship track and its albedo is a good percentage of them actually darkened, not brightened, because the liquid water path decreased in this case, and that drove the response. Some percentage of them showed no change in liquid water path, and that's what you would argue would be the Toomey effect in there, and some proportion of them showed a change in an increase in liquid water path, and the albedo brightened in that case. So the message here is that it's much more about the liquid water path change and what's affecting this water budget as a principal influence on why aerosol might influence warm clouds. Okay, I think I'm going to summarise here in the way of a table, and this is sort of leads into the talk I'm supposed to give in the next workshop tomorrow. Let me just sort of summarise and sort of capabilities and where we are. These are some of the cloud properties I think we might be interested in from a point of view of aerosol indirect effects. There may be some missing here, but let me just, for the sake of argument, just go through these. One of the things we'd like to know is the cloud base height of these shallow clouds. We have no capability at present, remotely sensing from space, to do this. The LiDAR cannot do it, and the radar on the A-train cannot do it. We have potential with spectroscopy of A-band, but that's a long story, more than I can talk about today. Optical depth, reflected sunlight, daytime only. There are some 3D biases in optical depth. Another method to get optical depth is the LiDAR transmission methods for thin clouds, particularly cirrus. This is daytime only, except obviously the LiDAR is more weighted towards nighttime. So optical depth we have reasonable outlook for that because these reflected sunlight measurements, we expect those to continue into the future. Cloud drop radius, reflected near-IR sunlight. These are column mean with differing weightings depending on which channel you use. The reason those particle sizes were different at 2.1 and 1.6 is the weighting functions are very different. So you're looking at different depths into the cloud. Cloud top temperature, these are IR radiance-based. Operational products exist and are expected to exist in the future. The cloud top height, LiDAR, we get also the IR cloud top temperature, but the LiDAR is our most definitive measure of the cloud top height. CLIPSO will end in about 2017, perhaps a little bit later, maybe 2018. EarthCare is supposed to kick into 2018, and the ACE Decadal Survey proposes the HSRL LiDAR, which would take place. Liquid water path, solar radiance and microwave radiance, the 30-year climatology I mentioned, and cloud radar. They all agree under managed conditions. The outlook would be CloudSat expect to run to about 2020, EarthCare 2018, as I said. There's more planning for decadal survey, and we have this slew of microwave operational instruments I should have listed there that's ongoing. Drizzle and rain, CloudSat, GPM won't collect the drizzle, EarthCare will, and the ACE mission proposed in decadal survey is what we're looking for beyond 2020. So we really have to rely on these cloud radars, I think, to get the drizzle process. Maybe we can get back from these drop radius measurements from motors and so forth with judicious kind of calibration of the system. Vertical motion, we have none. EarthCare will fly a Doppler radar. Its capability is about 1 metre a second, but about a footprint of several kilometres. So it's probably not in the game for these shallow warm clouds or even cirrus clouds and aerosol effects. So we've got a little ways to go. A Doppler radar concept for ISS is under consideration. It'll be more Doppler velocities for inside convection. The transition, I emphasise this, the transition from cloud to rain, it's not widely considered important, but I say it's essential for the AEI. Some capability when active and passive are combined. We saw that with those funny diagrams of optical depth and radar, and you see the transition from cloud to rain in those diagrams. You have some capability. The Earth capability, even to reproduce the A-train capabilities, are TBD. We still have to work out whether Earth is going to have good optical depth information from solar measurements. So that's basically it. So thank you.